Very nice talk. My question is, what happens if you try and simplify the problem from 3 dimensions down to 2 dimensions? I'm sure to some extent many of the interesting issues go away. Maybe there's enough left to still have something interesting to talk about. For instance, you talk about what you mean by the mean of in a rotation group, but what about the mean on the circle? And my impression is that you're saying, well, if I know where the mean direction is, your logarithmic map is basically arc length around the circle. And if you go all the way halfway around the circle in one direction, you're plus pi away from the initial direction. If you go around the other way, you're minus pi. And if you had a data point that was shifting very slightly on the wrong end of the circle, it would shift from a plus pi weight of value to a minus pi value. Is that right?
I'm not quite sure, as I haven't really looked at it. My co-author may have something to add.
So really we're using the fact here that the distributions are concentrated. Yeah. So any samples that you draw from your distribution would be close to 0. They wouldn't be far around the circle. So we're leveraging off of that.
Yeah.
The definition you gave of mean, did that involve a choice of basis for the algebras? Is that right?
So back this here.
That's the mean, is it?
M is the mean.
Okay, forget it.
So the condition on the distance that you give was AI, with the distance between AI and AJ less than something. So this is true for all I's and all J's? Or
This is true for, yes, I's and J's in general, that all motions in our set of...
So it's limited because that means that all of them should be very close to each other, not even pairwise. Like, it's more than pairwise.
So it is restricting in the general sense, yes, but if we look again at the applications that we're dealing with, these transformations are small, given that sensor data comes to us at such a quick rate. So as we move the probe, we have sensor frequencies of kilohertz of information.
And the other thing is that you don't specify a distance, so I mean, I can start at any distance and scale it become like this, no?
So we haven't thoroughly examined when does this algorithm, when does this method fall apart, at what length scale, if you will, or what distance between the rigid body transformations. So I can't quite comment on when exactly does it begin to degrade. We've done some initial look at it and we've seen that we can start to put a little bit, we can put reasonable distances and it still maintains its integrity.
It seems that it should be the distance which is related to the exponential.
So when dealing with rigid body motions, there's a natural way to define the metric. If I move a rigid body from one place to another, and you look at the Euclidean distance between every corresponding point on that body from the initial to the final, you can weight the norm of the log metric that we're using by the parameters of the rigid body that's being moved, and that's what we do.
Thank you again.